Okay, hello everyone. I'm Dorsa Sadigh, and I am one of the co-instructors of CS221. And today I'm here with Percy, Liang, and our group of TAs here to teach the first lecture of 221. So with that, I would like to first, before getting started in the details of the class, just introduce the team. So I am Dorsa Sadigh. I am an assistant professor in computer science. This is the fifth time I'm teaching CS221. The second time I'm teaching it online virtually. I think it is the third time I'm co-teaching with Percy Liang. So really excited to start the quarter with you guys here. And my research, just a little bit about my research. My work is in robotics and AI, and I'm in general very interested in the interaction between robotics and AI agents with humans and with other agents, other intelligent agents. So if these topics are of interest, come to office hours. We'd love to chat about that and talk about it offline in general too. My co-instructor today here is Percy Liang. I think I saw Percy somewhere on the chat.
Hello, everyone. I'm Percy. I'm the co-instructor. And I think this is my 9th or 10th year teaching 221. It's really been interesting how AI has evolved since when I first started talking about it. My research interests are in machine learning and natural language processing, thinking about how to make systems more robust and trustworthy. Recently, I've been really fascinated by what we've been calling foundation models, models such as GPT-3 and BERT and DALL-E, and happy to discuss that more later in the class.
All right. Thank you, Percy. All right, so what are we going to be talking about today? So our plan for today is to talk a little bit about some of the course logistics, and then some of the course contents, like what are we going to actually cover as part of this class. Then we'll have some icebreaker. So we'll have like a 5-minute breakout room. We'll discuss things about AI. And then toward the end of the class, I'm going to talk a little bit about the history of AI, a brief history of AI, and then what AI is today and what are some risks and benefits of AI and how we should think about it moving forward. So that is our plan for today. Okay. So before I start, also, if there are any questions, feel free to put questions on Zoom chat or raise your hand, and the CAs can try to kind of like answer the questions or like ask the questions like throughout as I give the talk. All right, so let's talk about course logistics. So we are going to have a set of activities as part of the class. And last year, when we had to go virtually because of COVID, we started experimenting with a few different ways of changing and reformatting the class. And some of them worked really well, and some of them actually didn't work so well. So based on the experience that we have from last year, we've decided to switch up the activities a little bit more. And also, like some of these changes really make sense to do also throughout like normal quarter two, even if you're not virtual. So one of these changes is going from traditional lectures to something that you're calling modules. So these are basically pre-recorded modules and lectures that are broken into small bite-sized chunks. So on every topic that we are going to cover in this class, we're going to have a lecture of like 10 to 20 minutes and a module really that goes over that topic. And these are pre-recorded, and you're going to release these like the modules for that week on the Monday of the week. So you have time to watch these kind of like based on your own schedule and when it makes sense for you to watch these lectures. So it's a little bit easier to manage these like bite-sized chunks. That's one reason that you're going towards these modules. Also, these are pre-recorded, and we're probably going to use the same recordings as last year. So we have more time to spend with you guys during our lecture times, kind of in a flipped format. Okay, so that's the modules. Then in addition to that, during our normal lecture time, we're going to have two types of activities. So on Mondays, we're going to have faculty chats. So these are going to be on Zoom. And they're basically small group discussions with faculty on AI-related topics. So they're going to be basically 6 like 25-minute sessions. So every Monday from 1:30 to 3 p.m. Percy and I, each of us, are going to have a Zoom room, like 30 minutes each for each session. And you're going to be assigned for one of these faculty chats. So this is actually mandatory to attend at least like one of these faculty chats. And the reason we are doing this is traditionally when we have a large AI course, like we have like 300 something enrollment, and it's really hard to get to know you guys and actually like talk to you. And sometimes it becomes like really difficult to know the faculty when you're in some of these larger classes. And this is really like what we are trying to do here is really to get to know you through some of these faculty chats and discuss like some of the AI related topics, some of the more recent material, research material around newer topics like foundation models that Percy is going to talk about, or some of the topics around robotics, autonomous driving, and so on. So I'll talk about this a little bit later in the talk, the exact format of it, and there is a little bit of a homework to do beforehand before coming to these sessions. But the idea is we'll have these virtual faculty chats on Mondays, lecture time. And one other point that I want to mention is that if you have conflicts during lecture times, you want to make sure that you wouldn't have conflict for the time that you're assigned. So it does actually, because that is mandatory. So make sure that you actually don't have conflicts during lecture times. All right. So the second bit is problem session. So this is going to be on Wednesdays. So on Wednesdays, again, during class time, we are going to have these problem sessions, and they're kind of like traditional sections, except for we have changed them a little bit based on the feedback that we got last year. And during these problem sessions, we're going to have the CAs work out practice problems. So these could be previous year's quizzes or previous year's exam questions, or basically just problems that can help you get started on your homework, or basically get ready for some of the exam questions later on. So I do recommend going to these problem sessions. They're incredibly useful to get your hands dirty with some of the topics that you're learning that week. And again, this is on Zoom on Wednesday's class time. All right, so what else? We are going to also have homework parties. So homework parties used to be very popular when they were in person. And last year, I think it was a little bit more difficult to make it happen, but eventually people realize that homework parties like matter a lot, because that's a very good place to show up and work with other people on your homework problems, get started on some of the more challenging problems together, study together, and the CAs will be there to answer questions. So these homework parties are going to happen on Nukes, which is a platform that we started using last year. Again, all the information about Zoom, Nukes, like all these links are is on the CS221 website. So the details of everything I say today is also on the website. Okay. All right, so beyond homework parties, we also have office hours. So the CAs have office hours, and there are two types of office hours. So there are a set of in-person office hours that I was talking about earlier. These are limited, but they're going to be in the basement of Huang. And they are group-based. There is no sign-up required, but basically there's a group of students and the CA at the basement of Huang. In addition to that, we also, the majority of office hours are actually going to be virtual. And these are by appointment. So we used Calendly last year, and part of it was just these queues were becoming too long to handle. So now we can make an appointment for a CA office hour. It's going to be a one-on-one office hour. And these office hours will happen on Nukes. Okay. In addition, our CA office hours are two categories. So we have separated general office hours from homework office hours. So if you have homework questions, you should just go to the dedicated homework office hours. But if you have more general questions about the course, if you're thinking about your project, if you're thinking about generally AI questions, you should go to the general office hours or the faculty office hours, basically. All right, so and then the final thing that we have is faculty office hours. So Percy and I, both of us, will have a 50-minute office hours weekly, and the schedule for this is also on the website, so you can take a look at that. Again, it's one-on-one. It is going to be virtual, and you can sign up for them beforehand and then come and chat with us. And again, all details is on the website. All right, so let me just see if there are any questions here. Does anyone have any questions? Should I look at chat? Okay, let me just quickly look at chat. So when do we know which faculty chat to attend? So we will be in touch about this soon. So actually on that, there is, I'll talk about this in a little bit, but basically there's a survey that you need to fill out by, I should know this, by Wednesday. Correct me if I'm wrong. By Wednesday?
Yeah, that's right. No, Wednesday.
Okay, by Wednesday, yeah. So that is basically to get your preferences on what faculty chats you would like to go, and then we'll also assign you after that to specific faculty chats. Okay. All right. Do we sign up for CA and faculty office hours through Nukes? So no, we will use Calendly for signing up, but we will use Nukes for answering questions. All right. Okay. All right, so if there are no more questions, let me go to the next slide. So now let's talk a little bit about prereqs. So this is a question that oftentimes comes up. So what are the prereqs for the class? So you need to have some programming background. It would be good if it is in Python. So these are some courses that are prereqs for this course. In addition to that, it's a good idea to have some math background. So discrete math CS123 is a prereq. And in addition to that, it would be a good idea to have some background in probability and linear algebra. So 109 and math 51. Okay, but in general, we want you guys to have general familiarity with these and have some mathematical rigor and general familiarity with probability, linear algebra, discrete math, these types of topics. We are not really expecting a very specific type of knowledge. For example, like in linear algebra, you'll learn about eigenvectors, but like we don't really like require the knowledge of eigenvectors in this class. So they're not specific topics that we are looking for, but generally you want to know math, you want to know programming, and come into class with that knowledge. And the reason is that this course is also fairly like fast paced. So you don't want to spend your time like learning Python or learning math. Through this class, your Python programming is going to improve, your math knowledge is going to improve, but you don't want to spend time learning these backgrounds, and you want to really spend all of your time learning AI. So if there are gaps, some people do catch up, it is possible, but again, you want to spend your time like learning AI. So we kind of like leave it to you guys to decide and move forward. And you might ask, okay, how do I decide? So we have a couple of things online that you can take a look at. So we have a set of modules that we recorded actually last year, and these are prereq modules. So these kind of provide refreshers of some of these topics. So definitely take a look at some of these prereq modules, and that gives you kind of like a good sense of what is required to know to come into this class. In addition to that, the first homework is based on foundations. And the first homework really gives you a good idea of what to expect as part of this class in terms of, again, programming and math knowledge coming in. So take a look at these before deciding if you want to skip a prereq or not. But in general, again, I do think it's a good idea to have these backgrounds coming into this class. All right. So let's then talk about grading a little bit. So grading is fairly straightforward. So we're going to have a set of homeworks. That's 55% of the grade. We're going to have 2 exams. So that is 40% of the grade. The faculty chats, we actually count participation as part of the grade. So that is 5%. And then projects, we are going to make that optional this year. So it's going to count towards extra credit. And then if you contribute to ED, so we're going to use ED this quarter as opposed to Piazza. If you contribute to ED, that is also going to give you some level of extra credit. Okay. And in general, you can take the class for letter grade or pass, no pass. That is also like your choice, basically. So now let's talk about each one of these components a little bit in more detail. So in terms of homeworks, we have 8 homeworks, and these 8 homeworks are a mix of programming questions and written questions. And the programming problems are mainly focused on a specific application. So like, for example, we might be looking at Blackjack as a game, or we might be looking at like Pac-Man as a game of Pac-Man, or various types of topics like car tracking. So there's a particular application that is used as part of the programming component of the homeworks. And these programming components, they're auto-graded. So and then there are a set of basically public and private tests. So you should definitely try out these public tests first. Make sure that you test this thoroughly, because the grading is very strict. It's based on auto grading, and you don't see all the tests. So that's kind of like the point that I was trying to make here. And then in addition to that, you have 7 total late days, and you can use maximum of 2 per homework. The reason for that is we want to release the homework solutions, so you can't use more than 2 late days for homeworks. Okay, so that is homeworks. Okay, so that's our plan for homeworks. The usual, we'll go with that. One other point that I want to add on homeworks is we are adding an extra addition to every single homework, which is an ethics component. So an ethics component is going to be added to all of our homeworks. It's a new addition that we are having this quarter. And we're also going to significantly change some of these homeworks to incorporate an ethics question into them. So we're trying to incorporate that throughout the class, throughout these homeworks. So that would be also an addition to consider this quarter. All right, so moving forward with exams. So this quarter, last year we decided to do a set of quizzes. This year we were not going to do the quizzes. I didn't really like, students don't really like it every week. So instead, we were going to have 2 exams. Okay, and the point of the exams is really to test the ability of your knowledge on working in new problems. It's not really to know like facts that we are teaching. It's more about like your knowledge of AI and if you can actually apply that to new problems. And all these problems are going to be written, so no coding. And you should take a look at like past exams to get a sense of like how these problems look like and what is the format of them. So each one of the exams is going to be 100 minutes, and these exams are going to be open book. So we actually have the dates for these exams already. They are going to be released in a 24-hour window. So they're going to be released on the first one is going to be released on October 29th at 3:15 p.m. And then it's going to be due the next day at 3:15 p.m. Pacific time. And similarly, we have exam 2 on December 8th. So it's 3:15 p.m. Pacific time is the time. Okay. All right. So we have these dates. If you have major conflicts with any of these dates, you should let us know by October 8th, which is week 3 of the class. In addition, we will not have any late days for these exams. Again, because we need to release solutions, we need to make sure it works for everyone. So no late days gets applied to the exams. And of course, no collaboration on the exams. So please do not talk about the exams on Ed. So like if you have done it, you're done with it, but there's still like time left within that 24-hour window. Do not post anything about the exam on Ed. Okay. All right. So that was exams. The last component that is mandatory as part of the class is the faculty chat participation. So as I was mentioning earlier, the goal of this is really discussing topics around AI, like related and new topics around AI. So fill out this initial survey that I was talking about by Wednesday, so that way we can start scheduling these. You're going to be assigned a session. Again, 6 sessions run in parallel on Mondays. And this is during class time on Mondays, so make sure that you can actually make that time. And then you should prepare before these sessions, and these sessions are going to be on different topics. So if they are on specific like research topics like robotics, autonomous driving, ethics, robustness, foundation models, we often have some related material that we release beforehand. Sometimes we had a set of fireside chats last year. It could be like that fireside chat to watch or talks last year. It could be basically that talk to watch beforehand. So you come to the session a little bit prepared, and we can talk about these topics. We also have another set of topics that are really about more thinking about academia versus industry, graduate school, thinking about like how you read a research paper. So some of these other components that are maybe not necessarily a particular research area. And again, you'll have some material for these reading material to have beforehand, so you come in again prepared. So the way we are looking at participation as part of these faculty chats is, as you come in, you should introduce yourself, and you should also share a little bit about your thoughts or your goals for that session. So you should actively participate in that 25-minute session. And we kind of expect that when we are thinking about participation and grading participation during these faculty chats. Okay. You will not be tested on the material that we are discussing on the faculty chats. So I also just wanted to mention that. All right. Do we need to attend one faculty chat session to get? Yes. So you will be assigned one faculty chat. If there is room, you can actually attend more faculty chats. We are potentially going to have more room based on the number of students who are enrolled, but we will be in touch on what are the availabilities and if you can attend more than one faculty chat. But yeah, you will be assigned one. Okay, so let me talk about the project also real quick. So the project this quarter is going to be optional. This is what we did last year too, because the course is virtual and we thought it could be it might be a little bit more difficult to find a team and work together. But regardless, like a lot of students did the project last year, and there are a lot of interesting ideas and projects came out of that, and it was really exciting to see like so many cool projects like during that quarter too. So I do recommend that you guys look into this closely, even though it is optional. So the idea is you want to choose a task where you can actually apply some of the ideas that you have learned as part of this class and use those techniques for that particular task. It's a little bit open-ended. You need to like decide what that task is, but that's also the beauty of it, right? You can pick anything and apply some of the AI techniques that we are learning for that. The idea is that you can work in groups of up to 4 people. And then you also have a set of milestones, like you need to fill out a project interest form, there's a proposal, progress report, and there's a video and final reports that you need to do. So if you decide to do the project and actually get the extra credit, you should do all these different, you should actually like pass through all these milestones and finish the project. Again, the task is completely open, but there are a set of well-defined steps that we expect you guys to have throughout the course for this project. So this includes things of the form of like defining the task or implementing your baselines and oracles and things of those form, or having a literature review, thinking about what your evaluation metrics are. And you will have a CA assigned to you if you decide to do a project. You will have a CA assigned to your group, and your CA can also walk you through some of these different components that you want to have as part of your project. And in addition to that, one other thing that we have added is a mandatory check-in meeting with your CA. So this is a 15-minute mandatory check-in meeting with your CA. We think this is really useful, and to make sure that you keep up with the project if you decide to do it. And in general, if you want to think about ideas for what to do for your project, or if you have some idea and you want to discuss it, definitely come to office hours. You can come to Percy and I's office hour, or like the CA's office hours, and discuss some of these questions. Okay. All right. And the last point that I want to mention on on logistics is the honor code. So I want to spend a little bit of time talking about this because this is really important. You guys don't want to deal with it. We don't want to deal with it. So let's just talk about it and get it out of the way. So especially this quarter, given that things are online, we do want you guys to collaborate. We do want you guys to discuss together, learn together, like think about problems together. But the write-up and the code needs to be independently. So you need to like write your code, you need to write up your solutions like independently based on your own thoughts and your own ideas. So please do not share code. Please do not share your write-ups with others. And don't look at anyone else's write-up or code, even if it is on internet and you found it. Like, do not look at these things. And then, yeah, do not post it online. Do not, like, if you're proud of your code, you shouldn't post it on GitHub. Do not do that. And in general, when you're debugging, try to look at like input-output behavior. You could be like going to homework parties and debugging your solutions with other people, and really just look at input-output behavior. Don't look at each other's code, and that way you'll be safe. But I do want to emphasize that we do run MOS periodically, and this will automatically like detect like if there is like matching between codes. And please like do not do that. MOS is really good. So yeah, so and every year we have a number of cases. And sometimes like we run these things mid-quarter. So I want to also emphasize that. And then you don't want to these things like, yeah, you don't want to go through these things like mid-quarter. And it's again, something that we don't want to deal with. We don't want to deal with. Let's just not do it. We're also changing a number of like homework questions, and we're adding like we are adapting things to make this a little bit easier on everyone. All right. Oh, and then the last point I want to make is on communication. So we're going to use Ed this quarter. So in general, if you have any questions, best idea is to put a public Ed post. That way, course staff, students, everyone can see it. And you have a broader group of people who can answer that question. And you can help, like, probably other people are thinking about that question too. So that's kind of a best way of communicating with us. If there is a private question, make a private Ed post, and that way the course staff can see it. And for example, if you have a question that can give away answers, it's a good idea to post that as a private post. And in general, if there are sensitive matters that you want to discuss or OAE accommodations, you should email this particular email address. This goes to only 4 people. This goes to Percy and I and Shiori and Faye, so our student liaison and our head CA. So if you have any sensitive matter, you should just send an email to this email list that goes to the 4 of us. In addition to that, we're going to have periodic surveys. We also have a welcome survey already on Canvas. So please take a look at that and fill that up. And that way we can start getting some feedback. And again, as the course is virtual, we would love to get more feedback, periodic feedback throughout the course. So it will be great to give us feedback, tell us what works, what doesn't work, so we can adapt. And again, all these details, everything I've said so far is on the course website. And with that, I can take any questions about logistics. I know I covered quite a bit on logistics. If anyone wants to just ask a question, that's probably easier too, because then I.
So, if so on the exam, if we're looking for a clarification, should we post that privately to add? Not at all, or should we email it? You know, as far as if we're assuming that it's not something that was supposed to give anything away, it's just supposed to be a clarification of what's intended by the question.
You should post a private post on Ed
Okay.
that only goes to the course staff. Yes.
So that, and also my related question. So the in and out, input output, that was a good guideline. But then as far as with the coding of Python, what about the use, you know, in terms of basic routines? Obviously not trying to copy codes wholesale, but as far as using things like Stack Overflow and others, as far as for obviously there's all the various things that can be used as sort of like you know, virtual tutorials and you know, various things that you want to accomplish with the Python that you're writing. I assume that as long as it's, you know, just little routines, that it's not a problem. The problem is when it's starting to be that you're taking somebody's idea wholesale.
Yeah, and in general, yeah. So try to write things like, yeah, yourself basically. Like when it comes to writing the code part of it, try to, like, you can get ideas, you can discuss the idea of it with other people, or you can look at like online forums for ideas. But when it comes to writing the code, try to just write it yourself. If there are specific like things that you're not sure of, like you should go to the CA office hours, or should go to our office hours, basically ask us like that specific instance, and we can talk about it then. Yeah. Okay. All right, so let's move forward. So now let's talk a little bit about the course content. Okay, so what are we discussing? What is AI? What are we going to be covering in this class? So in general, we are in AI, right? Like we are interested in solving realistic, complex problems that have a lot of messiness and uncertainty. And if you think about a complex problem, let's say routing cars like in a city with a lot of like complex settings that is happening in that city, how do you go about solving that question? Let's say the question is just routing the vehicles, right? Like you're not going to start just writing out code for it, right? Like you don't start from scratch and from like not really having a formalism to just directly code. That seems pretty difficult. And in general, there's a gap between the code or the software, the hardware that in general we developed as AI scientists, as engineers, and what is happening in reality. Like what is the real world with all the messiness and complexities that exist. And really what AI and what in this course is trying to do is to bridge that gap, to figure out how we can take some of these real world problems and make it simpler in a way that is manageable, so we can develop algorithms and code for it. And for that, we have a paradigm in this class that we would like to follow. And this paradigm has three different core components, three pillars. And these three pillars are the modeling, inference, and learning pillars. And I'm going to talk a little bit about these. So the idea is we take a very difficult problem, we model it, and then we develop inference algorithms for it. And then throughout this process, there could also be, the model could have a set of unknowns, and we use learning throughout to actually make our models better. So let me try to make this a little bit more clear moving forward. So let's go back to this real world problem that we were talking about, routing vehicles like in a city. Okay. So this is a big problem. And in general, I would like to have a formalism. So what modeling does is it takes that complex problem and it tries to come up with a formalism, with a mathematical way of thinking about that problem. And modeling, just by definition, is lossy, right? Like I'm not going to get all that complexity that exists in the real world, right? All models are wrong, but some are useful, right? So under that idea, of course, you're going to lose some of this complexity, but we're still going to come up with something that is somewhat useful for the goal that we have. Maybe I would like to find the shortest way of getting from one road to another road. And if that is my goal, I can basically maybe model this real world problem as a graph problem, where I have a bunch of edges and vertices, and my vertices here are maybe my locations like in the world, and then the edges are maybe the roads that connect them. Okay, so this would be a graph model that represents that real world problem. So we're going to spend quite a bit of time in this class talking about modeling. And then once I have a model, then I can start asking questions about that model, right? I can ask, well, what is the shortest path of getting from one node to another node? Or what is the most scenic path of getting from one region to another region? Or I might have different objectives that I would like to be able to optimize. And inference is really a way of trying to solve that problem and give us an answer to some of these questions that we have here. Okay, so how do we make predictions? How do we figure out like what is the right path to take in this problem is kind of like the thing that inference lets us get. And then finally, the last pillar is learning. And the way I want you to think of learning is that if you think about that model, right? Like we are oftentimes, you're not going to be able to write everything in that model with all the complexities. But all we can do is we can write a skeleton for what we're trying to do, maybe a graph. But that graph might not, like you might not know what are the weights on the edges. Like we might not be given the edge values here, because like that would be like too complicated to write, or we might just not have it like periods at the beginning. So we often have a model without parameters. And the goal of learning is to look at data and from data complete this model and add these parameters that were unknown at the beginning. So what learning is really doing is taking the complexity that we have in writing the specification, writing the model, and takes that away and puts that into data. And the fact that there is data, I can take that data and based on how good that data is, or based on what I can learn from that data, I would be able to complete my model and have a better model that I can actually do inference over. So we're going to have also learning throughout this class as a pillar in every section that we'll talk about in this class. Okay. All right, so modeling, inference, and learning are just three pillars that keep appearing throughout every week of this class. But what is our course plan? So our course plan is really to talk about different types of models, starting from low-level intelligence all the way to high-level intelligence. And we're going to basically go over a variety of these models. But before we start talking about these, we're going to actually spend 2 weeks talking about machine learning. So this is just to get some of the basics of machine learning out of the way. Also, machine learning in general is a very powerful tool that has been quite impactful in the field of AI. So it's a good idea to learn some of these ideas in machine learning at the beginning, so then we can actually also use it like throughout the class when we are thinking about learning, modeling, and inference throughout the class based on these different types of models that we'll discuss throughout. Okay, so next week and the week after is basically going to be modules on machine learning. Okay, I'm just spending a little bit of time on what is machine learning. So again, the role of machine learning is to take data, right, and from that data try to generate these models that were at the beginning incomplete, but now we can actually use them, and then we can actually incorporate the data, the information that's in that data in the model. And the idea of it is really moving from code to data. So again, adding like moving the complexity that exists in the code to complexity that exists in data. And one other point about machine learning is it requires faith, right? So we have some data. Based on that data, we build a model. There's no reason on the surface that model could work in a new scenario, that it could generalize to new settings. And then we'll talk about the idea of generalization quite a bit. Like, when is it that the model could generalize to new settings? Like, if I've trained it on some set of data of, let's say, like house prices, how can I make sure that this model could actually work in a new setting for a new house? And that kind of goes back to this question of generalization, and we'll spend time on that. All right, so that was machine learning. So as we were talking about machine learning in the first two weeks of the class, we're also going to spend a little bit of time talking about reflex-based models. So these are kind of the lowest level of intelligence in terms of the modeling paradigms that we'll be talking about throughout the course. And here's an example of a reflex-based model. So I'm going to ask you guys, what is this animal? Okay, maybe you can put in the chat, what is this animal, or just like shout. What was it? It was a zebra, right? And you were able to quickly figure out that you just saw a zebra here, right? And this is really based on your reflexes. This is really like an example of what a reflex-based model could do. Other examples of reflex-based models are things of the form of linear classifiers or deep neural networks. And the idea that I'm calling these like the reason I'm calling these low level intelligence is we're not doing a lot of reasoning here. We basically have a feed forward model, and you're not doing much computation into responding and saying, well, that was a zebra, right? Like we're just able to quickly say that was a zebra. And these reflex-based models, they're the most common form of models in machine learning. They're often like fully feed forward, no backtracking, no reasoning about what was going on, and just like evaluating the model. And deep neural networks are an example of this. Linear classifiers are an example of this. And that's actually the reason where we are going to discuss machine learning. We're going to also spend a little bit of time thinking about reflex-based models, where inference is extremely simple, and we just call it a model. All right, so moving along, on top of reflex-based models, the one level higher, we're going to talk about state-based models. And these state-based models, we're going to talk about three types of them: search problems, MVPs, and adversarial games. So what are state-based models? So here's an example. Let's say you want to play a game of chess, and you want to figure out what should be the next move of white. So this is not the same as detecting if that animal was a zebra. This is actually a lot more difficult than that. You actually need to sit down and do a little bit of reasoning and figure out what state in the world you're in, and figure out like how the world is going to evolve. So there is kind of like this notion of like sequences of actions and sequence of states that are coming after each other, like A leading to B and so on. And this kind of brings us to this idea of state-based models, and it has many applications, including in games. So if you think about games like chess, Go, Pac-Man, StarCraft, these are all examples where we can think about state-based models as a good way of modeling them. They show up in robotics all the time. If you think about motion planning, like getting your robot arm to move from one location to another location, we oftentimes use state-based models as a way of formalizing that. They also show up in natural language generation, machine translation, image captioning. They're basically like all throughout AI, and they're a very good way of thinking about like what are all the sufficient information that you need to know at the current time, and how that should evolve like in the next time step, and then adding an ordering of going from this state to the next state. So we'll talk about three types of state-based models. We'll talk about search problems, where you can actually control everything. So you have a state, and then based on the action that you take, you end up in a new state. We'll talk about Markov decision processes, which are making these search problems a little bit more difficult by adding uncertainty that comes from the world. So basically, these Markov decision processes are state-based models where you're playing against nature, right? Like nature gives you some probabilities. You look at like coin tosses, and based on that, you proceed. So there is kind of this notion of uncertainty. And then we'll spend some time talking about games, adversarial games, where you're not playing against nature, which is probabilistic. Instead, you're playing against another opponent, which is also very intelligent and is making decisions kind of like against you as opposed to you. And we'll basically go over these different types of state-based models a little bit. Okay, so and as part of the homework for state-based models, we're going to play around with the game of Pac-Man. I just want to show a quick demo of this game here. Yeah, so you're going to play around with the game of Pac-Man and basically come up with algorithms for Pac-Man who can avoid ghosts and eat these food pellets. And it'll be kind of fun playing around with it. And let me go back to my slides. Yeah, so and as you're thinking about Pac-Man and in general state-based models, the things to think about is what is a notion of states? How do you transition from one state to another? How can you come up with a strategy, a policy that can get you from one point to another so you avoid like the ghost and eat your food pellets and so on? And these are some of the questions that we're going to talk about when we discuss state-based models. All right, so moving forward, we're then going to move to the next level of complexity and intelligence, and not complexity, really intelligence, and that is variable-based models. So an example of variable-based model is something like a game of Sudoku. So if you think about state-based models, there's a notion of like sequential ordering of states. You have to do A to get to B. You have to go through A to get to B, right? Like if you think about like moving through a graph for solving like shortest path, you actually need to like see city 1 to and then after that see city 2. But there are a set of problems that don't really require that type of ordering, that type of strict ordering. So think of the game of Sudoku, right? Like the game of Sudoku, you have a bunch of numbers. You want to make sure that you can fit in like digits of 1 through 9 in every row and column. And the order that you put in these numbers, that doesn't really matter, right? Like you can put the 9s first, or you can put the 1s first, and that really doesn't matter. It doesn't really important. That really brings us this idea of variable-based models where we don't have this strict ordering. And because of that, maybe we can do something that's a little bit more intelligent and helps us come up with better algorithms in these settings. So we will talk about two types of variable-based models. We'll talk about constraint satisfaction problems. These are settings when we have hard constraints. So Sudoku was an example, right? Like you have a hard constraint, you have to actually fit like 1 through 9 in your board. Or like scheduling type problems, like a person cannot be at 2 places at the same time. So it actually has very strict relations between the different variables that exist. But in addition to that, we have also Bayesian networks that try to take those hard constraints and make them soft. So there are soft dependencies when you think about Bayesian networks, like unlike, let's say, Sudoku or scheduling. So an example is, let's say you want to track an airplane or you want to track a car, right? Like if you're tracking a car, you might have a set of sensors on that car, and those sensors are noisy. They're not going to give you the ground truth of where the car is. You also know that your car cannot like teleport, right? So the previous time step where it was and the current time step and the next time step, they're related to each other. And based on these different types of relations of where the car is and where the car is going to be, and the fact that you have these noisy sensor readings, you can have these soft dependencies between these variables, and that allows you to estimate where the car is. And that's a topic that we'll discuss like through Bayesian network. We'll have a homework on this that will actually be about tracking cars. That'll be exciting. All right, and then finally, the last component that we are going to discuss is going to be on logic. So this would bring us to the highest level of intelligence. And for logic, like as an instance of an example that uses logic, we can think of a virtual assistant. So think of a virtual assistant. What do you want from a virtual assistant? You oftentimes want to tell it some information, give it some information, and you also want to be able to ask it some questions, right? And expect it to respond. And maybe you would want to use like natural language as a way of communicating with this virtual assistant. So we actually go through a virtual assistant example as part of the homework in logic. I want to show a quick demo of that again here. Let me see if I can bring this to the right window. Let me go to the, let me see if I can bring terminal to this window. There you go. Okay, so this is actually a tool that we're going to play around with during the logic homework. Basically, it's a virtual assistant. You can give it information. You can ask it information. So let me try to some example. Let me actually give it some information. So I'm going to say Alice is a student. Okay.
Sorry, Dorsa, could you zoom in a little bit?
Oh yeah. How's that? Let me see if I can see a little bit more. Okay. All right. There you go. Okay. So I told it Alice is a student, and it just learned something. I can ask it now: is Alice a student? What should it say? It says yes, right? Because I just told it Alice is student. I'm going to ask, is Bob student? What should it respond? You should probably say, I don't know, right? Because how would it know? I don't know. Let me give it some facts. I can say students are people, okay? Then I can say Alice is not a person. Let's see what it says in response to that. Okay, it says, I don't buy that. So it understands contradiction. So I told the students are people, I showed a generalization, and now it's a contradiction to that, and it understands that. I can say Alice is a person. Let's see what that says. It confirms, I already knew that, okay. Let's give it some more information. Alice is from Phoenix, maybe. Let's do that. Okay. Alice is from Phoenix. I learned something. We can say Phoenix is a hot city. I learned something. You can say cities are places. I learned something. Let me actually make this a little bit smaller so you can see this. Okay, so if it is snowing, then it is cold. So I'm gonna teach it kind of like an if then else type of statement. I learned something. Okay, I'm gonna ask it, is it snowing? What should it say? Probably doesn't know. Right, so it says I don't know. Okay, so I'm gonna give it more information. If a person is from a hot place and it is cold, then she's not happy. Okay, so I'm giving it this more complicated if then else type statement. I learned something. I'm gonna ask, is it snowing? What would it say? Probably doesn't know, right? I don't know. I'm gonna say Alice is happy. Okay. Now I'm gonna ask, is it snowing? What should it say? Yes, it's not snowing. Yay. Yeah. So yeah, so this was just an example that was going over like this virtual assistant, and you'll play around with this virtual assistant. And in the logic module, you'll be thinking about this idea of giving information, asking information, and the logical relationships between them. And this will be something that we will work on. So I just want to quickly show this demo. But one thing to notice here is that here we were giving these kind of like heterogeneous information. This was very different from me giving like millions of pictures of cats and training a neural network, right? Like I was giving these very heterogeneous information, and the system was able to like reason about these information in a very deep way, right? Like it was making these deep connections, and I could ask these questions from it. And that's very exciting, right? Like being able to have these types of deep interactions between the symbols that we are providing it. All right, so that kind of brings us to the end of this module, where we are thinking about different types of models. And as a quick recap, right? In this class, we're going to talk about low-level intelligence all the way to high-level intelligence models, reflex-based models, state-based models, variable-based models, and logic. And in each one of these modules, we're going to talk about the usual paradigm that we have that tries to do modeling. So we'll talk about modeling in each one of these settings. And then we talk about inference. What are the different inference algorithms that we can use? And in addition to that, we talk about learning, right? Like how can we have data, and how can we learn and improve our models for each one of these components? So that paradigm keeps showing up throughout the class, basically every week. All right, so now let's spend 5 minutes and let's have an icebreaker. So it's going to put us in groups of 4 in breakout rooms. And during these 5 minutes, let's just try to introduce ourselves to others, and just to maybe set the stage, let's have a question and let's discuss a question. And the question is, what is the biggest benefit of AI, and what is the biggest risk of AI? And when you come back, try to like put that on chat, and we will discuss and go from there. Okay, so let's spend 5 minutes in breakout rooms. So it was good talking to some of you during the breakout rooms. Yeah. So maybe you can kind of like put some of your responses, some of the things that you discussed on chat, as a way of like just discussing some of them. Also, quick things, don't direct message me on chat. I'm like barely looking at chat. So if there are any questions, please ping the CAs or email me later on, or put questions on that. Okay, all right. So yeah, any biggest benefits, biggest risks? Anyone has thoughts? Okay. Thank you for starting this. Improving people's lives, tangible applications, virtual assistants, biggest risks, ML fairness, ethics. Yeah, so these are all like great points. I'm going to talk about them a little bit if you have time. But now let's continue with the kind of like next segment, where I want to give a little bit of a history of AI here. And this is going to be brief. I don't want to go into too much detail. This is not going to be a complete history. But I think it's a good idea to talk about this because it gives a little bit of like insights in terms of like why we are where we are today and how things shaped over time. So if you want to give a history of AI, like we can really like go back to 1950, and in 1950, Alan Turing put out his kind of like his landmark paper on computing machinery and intelligence. And in this paper, Alan Turing asked a question: can machines think? Okay, and he came up with his answer, which was the imitation game, which you might know as the Turing test. And then you guys might be familiar with the Turing test. The idea of the Turing test is that a machine can pass a Turing test if it is able to fool a person into thinking that it's actually a human. Okay, and this paper was really like foundational, like in a sense that it started allowing us to think about intelligence a lot more carefully, and actually try to formalize that in a better way. And it was kind of like one of the first works, one of the foundational works that it started thinking about, formalizing this idea of intelligence. And then we might argue on if Turing test is a good test or not in terms of measuring intelligence, and then might have various opinions on that, but that part of it is not really the part that matters. The part of it that matters is thinking about intelligence, being able to formalize it. And one other thing that Alan Turing actually provided in this paper was this idea of separating the question that you're trying to ask, the what, from the how. Like, how are we going to answer this question, right? Like Alan Turing came up with this idea of imitation game, and basically what this was giving us was this idea of object specification, right? This is the thing that we are trying to get. This is our specification that we are trying to get at. But how we do it, or how the machine really does it, like he didn't really specify that. And this modularity of specifying what we are trying to get and how we are trying to get at, this is really like a foundational idea that we have been also using in a lot of our algorithms, and we see throughout this class, like separating out the objective from the algorithm and how we're going about it is actually quite important, and is a very good foundational idea. And one interesting thing is that Turing also provided, like at the end of this paper, provided some ideas in terms of how we should go about it. And he talked about two different approaches. One was this very abstract way of going about this problem, kind of like a top-down view, kind of like how we would go about solving chess. And this is really related to this idea of symbolic AI that I'm going to talk about. And he also provided another potential way of going about this, which is like having machines that have sense organs, AKA sensors, and teach them like a child, right? And this idea of teaching a machine and getting that machine and have sensors on it and let it sense data, and from that data try to learn, that idea is very related to the idea of neural AI. So since this point, right, in 1950, where Turing put out this paper, there has been kind of like three different flavors of AI that has been around, right? There's symbolic AI, there's neural AI, and there's statistical AI. And I want to give a little bit of a brief history of each one of these. So let's start in 1956, and let's start with the story of symbolic AI. So this is the first type of AI, flavor of AI that I want to talk about. So the term AI really comes back to this age of 1956. And this is when McCarthy basically organized a workshop at Dartmouth College. So John McCarthy, he was a faculty at Stanford CS. He actually created the Stanford AI Lab. And he organized a workshop at Dartmouth College that summer. And he invited a lot of other big names like Marvin Minsky, Alan Newell, Herbert Simon. He invited all of these people. And the goal of this workshop was to think about intelligence, right? They had a very ambitious goal. They wanted to think about every aspect of learning and every feature of intelligence. And they wanted to model that so precisely so they can have a machine that could simulate that. And this is a very ambitious goal, right? And then they were really after generality. They wanted to figure out what are the general principles of intelligence and learning that they can really get, so they can have an artificial intelligence and an intelligent agent that can simulate that. And that was really exciting. And immediately after this workshop, all of these people went back their ways and they started producing really cool systems around this time. So this was really the birth of AI. And we started seeing a lot of early successes. So like 1952, Arthur Samuel put out one of these first checkers programs that was able to play at the level of an amateur, like play checker at the level of an amateur, which was really exciting. We also, in addition to that, we had in 1955, Newell and Simon came up with theorem, with kind of like one of the first theorem provers, and they basically had the system that could generally solve problems and solve theorems. they came up with a proof for a theorem that was actually a lot more elegant than what people had before. And they tried to publish a paper on this proof, but the paper got rejected because the reviewers thought the theorem already existed. But it was really exciting to be able to have systems that can prove theorems, that can play checkers, that can generally solve problems. And there were a lot of optimism, right? Like all these really famous people in the field, they all had a lot of optimism about what is possible with AI, right? Herbert Simon said machines will be capable within 20 years of doing any work a man can do. Marvin Minsky said within 10 years, the problem of artificial intelligence will be substantially solved. Claude Shannon said, I visualize a time when we will be to robots what dogs are to humans, and I'm rooting for the machines. So these are not like random people on the streets, right? These are like famous people, like founding fathers of AI. And these are like some of the optimism, overwhelming optimism that people had around that time, what we could actually do with these AI systems. And unfortunately, we started seeing very underwhelming results. So around this time, right, the government really cared about the problem of machine translation, and there was a lot of funding around it. And then we started seeing results that weren't very that were kind of underwhelming. And here is kind of a made up example, but the results were things of the form of you might have a text that says the spirit is willing, but the flesh is weak. And you might translate that to Russian and translate it back to English. And you would get a text that says the vodka is good, but the meat is rotten, which is not very good. And as we started seeing these results, right, like governments started putting out a report about how these results are not so great, and then they started cutting off funding for AI research. And this is around the same time that we started seeing the first winter of AI. So a lot of optimism wasn't really going anywhere, and we had this first winter of AI, and that wasn't so great. So if you think about this first early era of AI, what were some of the problems? So some of the problems were, well, first off, we had very limited computation. Like a lot of these problems were written as logical problems and usually like were solved as search problems, where the search space was just growing exponentially. And with the limited hardware that we had, it was just like not possible to solve these very difficult problems. But even if we had like infinite compute at that time, which we didn't, there was another problem. And this other problem was the fact that we had limited information, right? Like if you think about solving some of these very complex AI problems that people were thinking about, they needed to write out these problems and the knowledge that exists around them using words and objects and writing out the concepts. And it was very difficult to actually provide all these information. And we had really limited information about some of these concepts. But regardless, we started seeing a lot of interesting contributions that came out of this era. Even though it was a failure and we had this winter of AI, there were a lot of interesting ideas that came out around this time. Like we had the Lisp programming language, we had ideas like garbage collection and time sharing. And a lot of these ideas are associated actually to John McCarthy. But it was exciting to see a lot of advances, even though like the problems were still there and we couldn't really solve the big problem. And this really brings us to the era of 70s and 80s. So in 70s and 80s, really, people started thinking about this idea of knowledge and building knowledge-based systems. And kind of like the core idea was knowledge is really the key. If we can encode knowledge, if we can bring in ideas from experts and bring in domain knowledge and incorporate that in a system, then we can actually solve interesting AI questions. So this was the rise of expert systems, where we can basically elicit like domain-specific knowledge from an expert and encode that into like these if-then-else type statements, into rules that the system can call and be able to like solve various types of problems. There was also another shift around this time. So the first era of AI, right, the John McCarthy, like Dartmouth College, like workshop that happened, that was all about understanding intelligence, being able to say, well, what is human intelligence and can we simulate that? And that didn't really work out. But in this new era, what happened was people started kind of like changing and changing paradigms, and they started thinking about applications a lot more. So sure, we are not going to be able to think about intelligence and simulating intelligence, but I can build systems that can be used in chemistry, or they can be used in medical diagnosis, or they could be used in business. And this was kind of like a first era that people started building AI systems that maybe they weren't so much about simulating intelligence, but they were about solving interesting, useful problems that could be used in industry. So lots of wins during this time, right? So these knowledge-based systems, they really helped us with both the information and computation gap, right? They allowed us to incorporate knowledge and information. And by doing so, they allowed us to kind of like prune the search space. And that would help us need like less compute to solve some of these problems. So that was exciting. And this was the first time that we were seeing some of these real applications that actually impacted industry. And that was also that was also very exciting. But there were still some problems around this era. One of the problems was these rules were very deterministic and they couldn't really handle the uncertainty that existed in real world. You had all these deterministic connections and rules that were coming together, and they weren't really capturing the complexity of that exists in the world. In addition to that, the rules were becoming very complex very quickly. So this is a quote from Terry Winograd, who was a faculty in the HCI, in CS department in HCI at Stanford. And at the time, he was a faculty actually working in AI at MIT. And here's some quotes that he said around these knowledge-based systems. He said, well, these systems are a dead end and they have very complex interactions that are difficult to handle, and there are just really no easy footholds to have. And this really brings us to the second winter of AI. So lots of excitement, right? We were seeing real applications, but there was still quite a bit of difficulty into extending these systems. And this was kind of the end of like this era of symbolic AI, right? Symbolic AI really dominated AI for many decades. And I now want to go back in time, right? Like I'm now in 1987. But now I want to go back in time and tell you a little bit of a history of neural AI and where that started and what was kind of the progression of that. And that takes us to 1943. So going back in time, let's think about, okay, artificial neural networks and how they started. So in 1943, McCullough and Pitts, they came up with the first artificial neural network where they had a single neuron and they basically modeled that single neuron and they thought about very simple relations like ands and ors. And they weren't thinking about learning rules or anything of that form at that point. And that is kind of like 1943, the very first version of artificial neural networks. And in 1949, Hebb came up with the idea of coming up with a learning rule here. This learning rule was very simple. It was cells that fire together, wire together. And this learning rule, it was actually kind of like, it didn't really work and it wasn't very unstable, but it was one of the first learning rules that was put in place. And finally, in 1958, we started seeing some advances in artificial neural networks. This is when Rosenblatt came up with the perceptron algorithm for a single layer neural network, which is basically a linear classifier. And this perceptron algorithm was being used until very recently. And it showed a lot of success. It was actually very powerful. And there was a lot of excitement around it. 1959, we started seeing the analog of linear regression. That was Adeline. There was a multi-layer extension of that, Madeline. And this was actually used for removing echoes on phone lines. And this was, again, one of the very first times that people started using artificial neural networks for a real application, like removing echoes from a phone line. And 1969, that was an important year for artificial neural networks. So this year, Minsky and Packard wrote a book on artificial neural networks. They wrote a book called Perceptrons, and they basically tried to analyze mathematical properties of linear models. And the thing that they showed was actually something that was very simple, which is a single layer neural network is a linear classifier. It's actually not going to be able to solve the function of XOR. And this book is really associated to shutting down the research on artificial neural networks. Like that was a time that people started thinking maybe these types of artificial neural networks are not very powerful and maybe we should stop doing research on them, even though the book wasn't really saying anything about deep neural networks. Regardless, they started seeing a revival of neural networks and around 1980s. And this was kind of with the rise of convolutional neural networks. And the idea, like this came under the umbrella of connectionism. And we started seeing this very first convolutional neural networks, and the training of them was very ad hoc. But in 1986, that was kind of around the time that we started seeing better training and giving like more principled ways of training these systems. So around this time, Rumelhart, Hinton, and Williams, they popularized or kind of like reinvented the idea of backpropagation, and that was adding a lot more principle into how we should train these systems. And 1989, again, that was like one of the first times that we started seeing these systems being used in practice. So Jan LeCun applied convolutional neural networks for recognizing handwritten digits. And he actually deployed this with USPS for detecting digits of zip codes, which was really exciting. But still, this idea of artificial neural networks, it was still like a niche. Like it wasn't like a thing that everyone was working on. And that was until like the era of like deep learning and the 2010s like era. So, and part of the reason was it was actually really difficult to train these models. But in 2006, Hinton and al, they developed a system, an unsupervised layer-wise pre-training system that was helping pre-training some of these neural networks and kind of reducing the efforts that goes into training these models. But the break really happened around 2000. So 2012, we started seeing systems like AlexNet that were giving us huge gains in terms of object recognition. Like these systems basically revolutionized and transformed the field of computer vision overnight, right? The type of the computer vision course that I took in 2012 was actually pre-neural networks, and it was very different from like what is being taught today. And this basically changed the field like overnight with the rise of convolutional neural networks and training these systems and being able to do object recognition. And finally, in 2016, also we started seeing things like AlphaGo, like another breakthrough. And AlphaGo was basically using deep reinforcement learning to defeat like world champion Go player. And that was another breakthrough. That was a game that people were thinking was a lot more difficult, and it was really exciting to see deep learning and deep reinforcement learning is able to solve some of these problems. So, all right, so let me try to wrap up because I know it's almost 3 p.m. and we'll release modules on some of the rest of the lecture later today. But let me just give you some kind of like food for thoughts. I've talked about symbolic AI. I've talked about neural AI. The symbolic AI is really this top-down view that goes back, its roots goes back really to logic, right? Like we had these very big goals of building a virtual assistant. And neural AI, on the other hand, it's more like bottom up. It's trying to solve these perceptual tasks. And the two like might seem to have very philosophical differences, and they might seem contradictory, but they're actually not very contradictory. Like there are a lot of deeper connections between them. And today, actually, people are thinking about integrating them in ways that we weren't able to do before. And even if you go back to the history of it, right, like what McCullough and Pitts were doing with the first neural network was actually analyzing properties of a logical system. Or AlphaGo, if you think about AlphaGo, it's a very logical game that you can write like the rules of the game in logic, and it's using neural networks to solve that game. So there are deeper connections between these two views of AI, and they really come together. All right, so sorry for going over a little bit. What is left as part of this lecture is really talking a little bit about statistical AI. We'll release modules on these and thinking about where statistical AI is coming into play and wrapping up the history of AI. And then the other part that is really left is talking about AI and what are some risks and benefits of that. And that's something that you guys talked a little bit about during the breakout rooms. But we'll also talk about that in lecture. So if you want to watch these lectures later, that would be cool. And with that, I can, if there are any questions, I can take any questions. Otherwise, I'll see you guys next week.